One go to the same place. And yep, the rest will be the same thing. Yeah, always do well tonight. Do you live it all out there? That's all we have done. We got time to take a nap of the day. Alright, show up, or we move on. Okay. Okay, so last time, yeah, so we talked about the reaction of two reactions, adding and ketone. These are the wide range of nucleophiles. Now we have ketone can react. Okay, and if you count like how many reactions you have to learn. What did they tell you about the number of reactions you learn? They're not a lot. You have to group them together. You have to learn to group them. They have some similarities. Yeah, like alcohol, they do the same reaction. Fire is one. Any nitrogen nucleophile, carbon, and hydrogen. Right? And there are two types of the two patterns. Basically, there are two patterns, so we can run the reaction in acidic solution or basic solution. In acidic, because the hormone theory, something happened, and then hormone back. Or like that. They might repeat two times, three times, like that. For basic solution, you already start with a strong nucleophile. Nucleophile can attack right away, so you have nucleophile attack followed by some form of coordination. Coordination or decoordination. Okay, and the common mistake that I told you in basic solution, you should not draw what species?
H3O.
Yeah, you can't have you cannot really have it in acidic solution, and vice versa in acidic solution, do not draw. Okay, so it doesn't make an acid with cannot in acidic solution. All right. Two reactions last time. The first reaction is called acetyl hydration. We actually use water. So we got a pattern. We have protons in. Something happened. The protons out. Right. In acetyl formation, so alcohol react twice. So we have first alcohol gets in, second alcohol gets in. And you get acetyl. Add to any acetyl intermediate and end up with acetyl two alcohols. Before we move further, let me ask you this question. Alcohol reacts twice on ketone and aldehyde. Did you get what I just said? Alcohol reacts twice. Okay. How come? I'm going to go back on slide. How come water reacts once? I'm going to go forward to the acetyl formation. Can you see the alcohol attack? Alcohol attack. You get to alcohol. See that? Get to alcohol. Now go back one time. Go back one time. Water attack. That's it. But that's water not react twice. Yeah, think about it now. Let's look at alcohol first. Okay, how does alcohol react twice? Now watch. The first attack, you get the heavy acetal. Now the second attack, water leads. Can you see that? Water leads and another alcohol attack. Okay. Now go back right here. So the first alcohol attack. All right. So you get this is kind of heavy acetal. Right? It is if the another molecule of water were to attack. I have to coordinate one of these oxygen. Does that make sense? And it's going to leave. One of leave, another water molecule attack. What do you get? Same thing. Okay, so water can react twice. It can, but there's no point in drawing the second attack because you get the same product, right? You already start with one oxygen. That's going to turn to be one OH. That doesn't be a water. Add another water, you get another OH. In the case of alcohol, first alcohol, they don't look the same. It's like you can add another one. Okay. But water, alcohol, they have similar property, so they do whatever they do the same. So water can react twice, but it's no point drawing matrices. Okay. And we use ethylene glycol, so you can see one molecule but two alcohol in the same molecule. We add alcohol ketone, we get cyclic acetal. What do we use cyclic acetal for? Okay. What condition is cyclic acetal stable. It's a basic acidic condition. Okay, cyclic acetal stable. The CO bond, it either bond stable under basic condition, so you can do reaction under basic condition. We'll talk about this later. Use this again when we use synthesis. If you use it under acidic condition, clear this guy. Okay, no, we go back to the picture. That's how we do it. Okay, I have prepared video. Alright, under basic condition. If you want to remove it, use acid. Our next one, we're going to move on to nitrogen. Yeah, we're going to do nitrogen before. Wow. So the first one we have the imine. We make an imine. Imine is a compound that have C and double bond. There's another term called chip space or that you go. Yeah, it's called this class compound. Yeah. Anyway, we just call it imine in this class. All right. How it works? So we start with aldehyde ketone, same thing. All reactions in this chapter we start with aldehyde ketone. Add an amine. What type of amine is it? Primary, secondary, tertiary? Primary amines. Yeah, so we're adding primary amine, and we add small amount of acid. Okay, I'm going to walk you through how this reaction works. Okay. All right, let's start with this. Ignore aldehyde ketone for now. Just mixture of these two. I have a solution contain methylamine. There's a bunch of methylamine. And then I'm going to add small amount of acid, catalytic amount. How much is catalytic amount? We talk a few times. A little. It's a liquid, right? A few drops. Okay. So I'm going to add a juice like HCl. A few drops. Okay, so drop into it. What's going to happen to some of this? Some of them get protonated. Not all of them, just catalytic amount, right? Some of them get protonated. Okay, and put it in the formula, right? Now, are we adding water in this solution? Are we adding water in this solution? A little, not a lot. If you use concentrated sulfuric acid here, not a lot of water. Okay, so is there hydrogen ion in this solution? Easy answer. Look right there. Is there a hydrogen ion in the solution? No. So in the reaction, this reaction particularly, you cannot use hydrogen ion. Are you guys following? But we don't add. You can't just make it stuff, right? We don't add water. There's no hydrogen ion. So the identity of the acid is this guy, the ammonium ion. That's an acid, not hydrogen. We don't have hydrogen ion. That's no water. Okay. So the first step, when you usually do when you do a protonation, okay, when you do protonation, of course, you're not going to use hydrogen ion. You're going to use the quaternary ammonium ion. Then yes. All right. Before you do anything, look at the equilibrium. We're going to go back to Auto 1. Okay. So still remember how to determine the directional equilibrium? Does it favor the product or the reactant? Does it favor the product or go backward, favor the reactant? All right, let's check. Okay. pKa. pKa. Oh my God. Oh, 9 to 10. That's 9 to 10. What about that one? That's one low. Good. -7, -8. Okay. So if you look at favor, which one? Which side? Reactant or the product? The reactant. What's the KEQ? K 10 to the -17. This is go backward. This is -17. If the KEQ is 10 to the -17, do you think that this guy will get protonated? It's not favorable. By how much? 10 to the millions times. A million to the 6, right? It's almost 10 to the 18. 10 to the -18. So favor this way. How many molecules will get protonated? Not a lot. Not a lot at all. Okay? So for this reason, we don't have hydrogen ion, right? If this was to be hydrogen ion here, you're gonna get protonated form. That's fine, right? But this is not a hydrogen ion. Therefore, the first step of this reaction is not proton transfer, it's a nucleophile. You don't have anything to protonate it. You saw earlier by yourself, the protonation doesn't work. Okay, so the first is going to be the nucleophilic attack, not coordination. Okay. All right, next one. When you see this intermediate, now answer my question. When you see the oxide, what do you think happened to that oxygen? I want you to answer. What do you think happened to that oxygen? You will get chlorinated, right? Anything charged has to become have to become the neutral. Does that make sense to you? Everything will go to neutral. And what do you think would happen to the nitrogen later? Becomes dechlorinated. Okay, so you do either do one of them. So I'm gonna take the acid in this solution, which is not hydrogen ion. Mentioned a few times already. So we take the ammonium ion, so chlorination. Okay, and then we're gonna dechlorinate that ammonium ion. What's the base in this solution? Just an amine. We add a bunch of amine. That's the base. We use the solvent too. Okay, and also a base to add as a base too. Right, we get halfway. We used to call this the heavy acetal. Okay, in this case, look, it's kind of like heavy acetal. If it's supposed to be an alcohol or an amine, right? So you get heavy acetal. But this case, we have amine, we call carbon. It's just a different name, but the same thing. That's halfway. Okay, all right, we halfway now. Okay, we halfway now. Now, next one, I'm gonna try to go to imine. This is imine. Okay, I have to get rid of oxygen. Can you see that? That oxygen gonna go. But I think you guys know oxygen, like this is always alcohol. Is it a good living group? No. No. What do you have to do? You have to throw it. Okay. What's the acid in this solution? Go back to that guy. That's an acid. That's the only acid you have. It's not going to be favorable, but you have no other option. Okay, so we fluorinate that oxygen, right? And then we're going to kick that oxygen off with the lone pair of nitrogen, push the lone pair, kick it up. Right? And lastly, when you see this, what do you think happens? The chlorination goes off that hydrogen. Okay, I'm going to give you some more examples. Hopefully, you will see the pattern. This is the first one. Yeah, but the bottom line, take a look. Protons in, protons out. Protons in, whatever happened, protons out. Can you see that? They got the same patterns. Okay, this is the case that nucleophilic attack started at the beginning, but proton transfer is slow. Normally, proton transfer, as you mentioned, is the fastest reaction in the field. It depends on the situation, not in this case. Okay, this reaction is highly pH dependent. The rate changes after pH changes. Okay, the fast rate for this reaction only. Okay, they do the research. pH 4.5 makes this reaction the fastest. Okay, too acidic than that, too basic than that, the rate is slower. Here's the reason why. All right, let's take a look. Higher pH, 6, 7, 8, 9, 10, 11, 12, like really basic side. Okay, now answer this question first. If the solution is basic, what species what species is abundant? Yeah, what species is abundant? Basic condition. It can be imagined hydroxide ion. It doesn't have to be hydroxide, but like the solution is basic. Imagine hydroxide. Okay, let's say a bunch of sodium hydroxide, fluoride in solution, fluoride in solution. All right, stay with me. Okay, now let's say in this solution, well, that with sodium hydroxide, a bunch of hydroxide floating around, you expect the rate. Some of the steps will become very slow. Which one? Anything that involves acid. Does that make sense? Right? Look for proton transfer. How many proton transfer are there? Chlorination. How many chlorination are there? One, right? At least that one. Okay. If there are a bunch of hydroxide in this solution, we're not going to have a lot of this guy. Does that make sense? So that's an acid. Hydroxide attack first. Okay. That's why the reaction becomes slower. This that's another one. That is next to you all. Okay. So this reaction is very pH dependent. Too much hydroxide. the proton transfer is slow. Now, on the other end of the spectrum, low pH. What species abundant in that low pH? Hydrogen ion. Imagine you add hydrochloric acid, a bunch of sulfuric acid into it. Okay, so some of this are going to be slow. Which one? That involve for example, this there, one of them, okay, is going to be slow. Imagine if there are too many the hydrogen ion going in the solution, we're not going to have a bunch of amine available to attack. Okay, so not a lot of that amine, low starting material, reaction slow. Of course, it will affect that one too, same thing proton transfer, but proton transfer usually faster. You can apply some of the rate determining step. The rate determining step probably does. Depending on pH. I know there's a lot of things going on here. Yeah, so the first step, not a proton transfer, it's a nucleophilic attack. Proton transfer, the bed weak, that's weak. Not favorable. Okay, and it's very pH dependent, too basic, too acidic, some gets that very slow. Right? How about grab a pen, grab a pen. If you look at the handout, I want you to draw arrows. Can you draw arrows to track the mechanism, complete that mechanism? And you can guess, I'm sure you can guess. The first, and here's the first one. Yeah? A level thing for you. You get 5 in the rate. Check with me, okay? So today I give you the intermediate and the product. All you have to do is draw an arrow, right? But on the real time, on the exam, you have nothing, right? So you have to be able to draw the mechanism on your own. But now, let me walk you through. Each step should tell you, should give you a hint what you have to do. Okay? The first step, so the first step is a nucleophilic attack. You guys get that? All right, so we have 5 add-ons, so you get form of 5 member 3. Okay, so you get the one of the intermediate look like that. Now, answer my question. All right, we're going to keep going from here. What do you think would happen to that oxide? Chlorination. And what do you think would happen to that nitrogen? Chlorination. What do you guess on here? Can you see that? All this you can guess. Okay. Now, this is going to be proton transfer. Start with the oxide. Okay, the oxides. Right. Now, from now on, you're going to see a bunch of proton transfer. So on exam, you are allowed to draw PT like that and put a proton right here. 7 times. Okay. However, That's a price we have to pay in order to do that. Okay. So if I'm adding proton on here, what is the source of the acid in this solution? There'll be a few times, just let you know, there'll be a few times you cannot do proton conversion. Yes, people students like drawing proton conversion, proton conversion. What's the base? You need to have that. So what's the identity of the acid in this solution? Do we add water? Is there water in the solution? No, you cannot use hydrogen ion. What do? It's a protonated version of pyridine. We call pyridinium ion. We add these two together. Okay, so it's that. Alright? So this guy's gonna go grab a base, grab a proton from the pyridinium ion, and then you get that hydrogen. That's a logic. Make sense, you all? No water, you cannot use hydrogen ion. Okay? We have pyridine and an acid. Here we go. Pyridinium ion. Alright, we have the nitrogen to go. We got nitrogen to go, so we have to deprotonate that. What's the base? We need a base. Pyridine, we take pyridine. Okay, so take pyridine, attack the proton. There we go. We halfway carbonyl. Okay. All right, from carbonylamine, we're gonna go to the product. Okay, so oxygen, this guy gonna leave. How do you make it leave? Yes. Protonated, yep. Convert to a better lead group, so we protonated because the only acid we have is pyridinium ion, so protonate that. Now that guy can leave now. Okay, so use a lone pair, push it out. Okay. We're almost done. What do you think would happen to that nitrogen? Deprotonation. Can you see? You can guess this, right? That's a clue that you can guess. Not just like drawing mechanism line. That's a clue. Everything tries to be stable. Charge is not stable. You get rid of the charge. Okay. All right. That's imine formation. Okay. So we have aldehyde ketone react with what type of amine is this? Primary, secondary, tertiary. This is primary. This is primary. Primary. Okay. There are other types of primary amines you can use. For example, we have amine next to the oxygen. We call hydroxylamine. You don't need to know the name. Okay. Another one we have hydrazine, two nitrogen next to each other like that. Right? Hydroxylamine react with aldehyde ketone. Give a compound called oxime. Hydrazine gives you hydrazone. Again, you don't need to know. The hydrazine reaction in all time they use this reaction to qualitatively identify an unknown solution if that unknown solution has aldehyde ketone or not. Okay, so they take this compound to form dinitrophenol hydrazine. They react to the any kind of ketone aldehyde, and the product got color look like this guy. That's how they do the test. I'm not sure if the unknown compound has aldehyde ketone. Right, let's add a few drops of 2,4-dimethyl hydrazine and see if it shows colors. It precipitates this color. Okay. Anyway, so that's just on the side. Okay. All right. Hydroxylamine give you oxygen, hydrazine give you hydrazone. All right, look at this one. Okay. From hydrazone, this is what you're gonna do. From hydrazone, you can remove the two nitrogen altogether by doing this reaction. We call it Wolff-Kishner reaction, and you get it out there. Have you seen something a reaction that you do something like this? What reaction is that? Using nitrogen. Come on, you gotta link the connection. Have you seen any reaction that do like this? We have a ketone, and then you have no ketone.
Oxidation.
Clemson reduction. Good job. This is Clemson reduction. You will see it tonight anyway. Okay. The Wolff-Kishner reduction is more favorable in the lab. I'll tell you why. Okay, I'll tell you why. But I you learned it last night, right? Yeah, you learned it last night. Come on. Okay. All right. Beta carotene. Okay. When you were younger, all people usually tell you eat carrots. Why?
To make your eyes healthier.
Make your eyes what?
Healthier.
Healthier. I heard you say prettier. Eat carrots. Anyway, what does it do to your eyes though? No, what about it? Okay, so this is where I can achieve. You guys have healthy eyes, right? At night you can see things like that. If your parents, your grandparents, their eyes are not that healthy, that's what they see called night blindness. Some people, not everyone, of course, some people. Okay, and night blindness could be from genetics, could be from the aging, or could be from lack of beta carotene or vitamin C. Beta carotene is not vitamin C, right? Anyway, so beta carotene can be obtained from this type of fruit and vegetable. Anything that's shown is the orange color. When you did the lab a week ago, I think you get like beta carotene, right? Is it orange in color? What color?
The orange.
Depends on the concentration. I think some you get yellow, right? Something like that. Okay. Anyway, beta carotene, the concentrated one is orange. Okay. All right. Beta carotene. If you consume beta carotene, you will get metabolized for everything, more thing for the liver, right? And get it cut, right? Get cut in half, become redness. No, redness. That's vitamin. Yeah, what vitamin B comes from. Okay. All right. Look at this functional group. This is we call alcohol. What can you do with alcohol? Come on, you learn it. What reaction you can do with alcohol? I'm waiting for that reaction. Dehydration, that's I'm looking for, but yeah. What else?
Williams ether.
What is that? Ether, that's ether. Let's look at alcohol. Alcohol synthesis, something like that. Oh, come on. PCC, sodium dichromate. What reaction is that? We call oxidation, right? Ah, there we go. Yeah. We call enzyme oxidase. Well, oxidation. That's what we call it. Oxidation. Right? That also the chemical. We human imitate enzyme. Okay, enzyme is included for the beginning of enzyme. Yeah, we imitate that. We have what the enzyme to do that too. Also the guy that technically brought the aldehyde too. Anyway, all right. This one called all trans remnants. Yeah, look at that. This is number one. I summarize. What's the name of the enzyme that I summarize this compound to 6? What do we call it? Isomerization. What do we call the enzyme? Isomerization. That's it. Oxidation. How do you do it? Okay. Well, enzyme called isomerase. Okay. So convert the all trans to 11 branch. Now that's from the liver. Now this compound gets sent to your eyes. Your eyes do some reaction to. We have a protein called opsin. What type of amine is that? Primary, secondary, tertiary. Because primary amine. We have aldehyde. This reaction called imine formation. Have you learned that? You just learn it. You don't draw the mechanism to why. Right? We are right here, so you get it imine. Okay. We call this protein. It's a adductor protein. Addition product protein. We call rhodopsin. Rudolph. Not the Rudolph. The brain over here. Okay. This is it's green means rose. It's pink in color. This protein is pink. Anyway, once you go outside, any light source, okay, any light bulb will convert the cis to trans. That's light energy. And we got the enzyme. Go back there, grab the whole thing, cross it back to 6. This transformation, not transformation, this isomerization shows some they call it the movement in protein opsin, and your brain can detect that. When your brain detect it, it converts that to be addition. Okay, and rhodopsin is predominant in rhodopsin. People who have low vitamin A level, they probably they are risk of having microbes. Okay, so information. Next one, enamine. Check. We just saw the reactions where primary amine react with ketone and aldehyde. You get enamine. Now we're going to move on to secondary amine. Okay, this is secondary amine. The product. Look at the product. The product contains both alkene and amine. We call it enamine. Can you see the difference? The first one we call enamine. This one enamine. Oh, come on. Some of the names were not some use. Anyway, all right. So Look at the mechanism, okay? So we just drill, I'm gonna compare contrast. Have you played that game, like two identical pictures, and you have to like point out that different, that. We'll do that, okay? All right. So we have this is the mechanism we do together. This one, imine, okay? Primary amine reaction, we just did together. This is enamine. What's the difference? Besides secondary amine, but what's the difference? Which step is different? The last step, but we compare just the last step. All right, make sure you know the logic. Make sure you know the logic. Listen, okay? Look at the top one. The top one we do together. What's the purpose of deprotonation? What is that for? What do we do for deprotonation at the end? Get rid of positive, right? Positive charge is not stable. We try to get rid of the charge. What do you do? There's a acidic proton right there. Deprotonation, you get neutral compound that's stable. However, secondary amine doesn't have luxury of having that extra proton, right? We need to get rid of the charge too. The only available proton is the one next one, the beta proton, beta hydrogen. That's why this reaction is called elimination, not deprotonation. That's the only option it has. Yeah, everything else is the same. Everything else is the same, except the last one. Secondary does not have that proton. Okay, so you have to find proton elsewhere. That's why we have elimination, not deprotonation. That's only the difference. That's it. Okay. Does this make sense to you all? Hopefully it does. Okay? Everything gonna make sense in science. Right? Everything has to make sense in here. There is a reason why things happen. Okay, pretty much it. Nitrogen profile. They are going to either primary amine attack or secondary amine attack. One gives you amine, the other one gives you enamine. Okay, mechanism is almost identical except the last. Okay. All right. Well, we have book Kirchner with I just left that out. So go back to the imine formation of hydrazine, you get hydrazone. We can remove the whole thing, right? And you get the alkyl chain. Okay. This one is similar to clinical reduction. In the lab, we prefer book Kirchner reduction over clinical reduction. Here's the reason why. In clinical reduction, do you remember what you asked beside it? What else? SPR, what else? Same add one more. Mercury. The problem is mercury. I think some of you know mercury is liquid and highly toxic metal. Right? So in the lab, whatever we do, we try to avoid using mercury. Any reaction, anything you do, we try to avoid. You know that the old thermometer used to have mercury in it. But some of you know, okay, right now it's not mercury anymore. Right now it's alcohol. Because we try to avoid mercury and keep undergrad break things, right? And mercury is everywhere on the floor, on the bench, so it's hard to like take it out the mercury. So anyway, my point is we try to avoid mercury. So book Kirchner, milder reaction, yeah. So you don't need to use mercury, less toxic. Right? So we try to use book Kirchner better than clinical reduction. Anyway, now what? We talk about the mechanism of the first one, this information. We'll talk about the mechanism of the last one. All right. So look at this too. This is not a complete reaction yet. What else is the byproduct? I have you guess. What else is the byproduct? From second step, from this hydrazone to the product, what else come out here too? It's nitrogen gas. Any reaction that creates gas, this reaction is highly favorable. But when gas is stable, gas bubble out of solution, the product is getting taken away. The equilibrium drive forward. Okay. All right. The mechanism will be more like this. Okay. Before I show you the mechanism, let me ask you first. Look at the nitrogen gas. What is the bond? What type of bond is in between that two nitrogen? Single bond, triple bond. Okay. So basically, this mechanism, you're gonna form triple bond right here. Are you following? Right now we have single bond. You're gonna form two more pi bonds. Is everyone following? Okay, all right. We try to create a triple bond. So we have to form two more pi bonds. What reaction allows you to form pi bonds? Elimination. Yes. How many elimination you have to do? Two times. I'm going to show you we do elimination two times. Okay. Go back to the old start. Right. This is here. This is reaction. All right. Here's the first one. Acidic proton, add hydroxide, heat up, speed up the reaction. So first elimination. Not like elimination yet. All right. I'm gonna draw the resonance structure. Put number one right there. Push number one down here. Okay. Negative charge will protonate it with solvent, water. Here we go. We have another one. I'll have you guess what happened right after. How many elimination we have to do? Two total. That's one. You do one more time. You do one more time. Okay, like one more time. Okay. You can put the in this case you can put the negative charge on nitrogen because nitrogen is electronegative. They can hold negative charge. This is fine. You can like oxide, oxygen. Anyway, for triple bond and this guy leaving as nitrogen gas. Irreversible. Back after the reaction proceed, nitrogen gas keep bubbling out of solution. Yeah, the equilibrium goes forward. All right, the last step, protonation, take water, protonation. That's it. Okay. After the exam, maybe this weekend, we're gonna go to second note. So make sure you understand what each step is for. Okay. How many eliminations you have to do? Why do you have to do elimination? Right? Something like that. There's a logic behind each mechanism. All right. We've been talking about the mechanism. So on exam, I can ask you to predict products. Do not attempt drawing mechanism for each one of them. You don't have time. Okay, this is not the place to draw the mechanism unless I ask you to. If I don't ask you, do not draw the mechanism. It's too long. You don't have space to. Okay, all right, but this is gonna look something like this. By this weekend, by next Monday, you should be able to do this. When you see this reaction, if you draw the mechanism often enough, the mechanism should pop up in the case, for example. Okay, so this is ethanol. Ethanol will react with aldehyde ketone twice. Are you guys following? The first time you get the halfway, we call heavy acetal. Half alcohol, half water. Okay, and then the water gonna be gone. This guy gonna kick the water out, and then another molecule ethanol attack. Then you're gonna get natural product. You should be able to visualize the mechanism like that, but that's next week. That's what I wanted you to be able to do. Okay, right now all you have to do is react twice, show them like that. It's fine. Okay. All right. I'm gonna walk you through one more time. So look at this one. This compound is the one molecule plus 2 alcohol, right? Can you imagine the halfway the heavy acetal? What's it look like? That is heavy acetal. One alcohol group gets in first. Okay. And the next one, water gonna come off. The other alcohol attack. You get it first. You should be able to visualize like that. And that depends on how much you're familiar with the reaction, how much you have drawn the mechanism. Okay, mechanism is going to be really redundant. But you have to draw it like this is not this is not again. Come on. Don't be like that. Okay, next one down below. What type of amine is this? This is primary amine. Okay, you're gonna get the amine, CN double bond. Okay, all right. First attack, you're gonna get to halfway carbonylamine. Look like that. Water get kicked off, and the nitrogen form a double bond. Here we go. They all have the same patterns. They all have the same patterns. Okay. One more, two more down below. So this one, this is secondary amine. You follow it? What do we call the product? What's the product called? Yeah, it's E, not enemy. I know it looks like enemy. It's E, alkene. It's enemy. Okay, it's enemy. Okay. All right. So we're gonna make it enemy. All right. So the first this attack, you're gonna get the nitrogen like that carbon halfway. Water gets kicked out, nitrogen comes up double bond, but the double bond right here, you get a positive charge on that nitrogen. So you have to do elimination to get rid of that charge. Remember the last step? That's the last step of the CNB formation. Okay, and the product is we have E when we now CNB. Okay, if you don't follow that, it's fine. You have to go back home, draw the mechanism out, right? You familiar the mechanism. Understand how each reaction works, and this one it won't be a problem. I'm sure you'll be fine. And most of them are fine in this chapter. Okay, they all have the same patterns. All right, last one. Do you recognize this reaction? What does the second one do? I have to guess. Remember the reaction, we call Wolff-Kishner reaction? You don't need to know the name, right? But basically, you remove the ketone. Okay? All right, the first one, hydrogen attack. You're going to get hydrazone. Look like that? That's the hydrazone. And then Wolff-Kishner has that one right away. Remove the whole thing, you get hydrogen gas coming out. Like thermal reduction. Okay. All right. All right. Question on we've got 4 reactions so far. Yes.
You're reducing it, you have to do step 1 if you're going to reduce it. So does it only work?
The step 1 is for to make hydrazone. This one work we have to react directly to the ketone. Yeah, not like thermal hit right away, right? But this one you have to make the hydrazone first. This guy work with the hydrazone. You need the hydrogen gas coming off. Okay. All right. We're gonna 3 more reactions, but it's actually 1. Okay. We call it acetyl halide hydrolysis or acetal, imine, and enamines. All of them. Yeah, they have the same patterns. Hydrolysis means reaction with water, lysis means nothing. The way I have the acetal bond, imine bond, the second double bond, and then enamine bond. Okay. So I think you guys remember. So if you want to remove this protective group, we add an acid. It's stable under basic condition, but not under acidic condition. And so same thing. Acetal, imine, enamine. You can cut them off, adding acid, and you would flood in water. Okay. We use acetal as a protective group. Work only when it's under basic condition, stable. But once you add an acid, it's like it's a pop off. Okay. All right. When you draw out the mechanism, in this case, look at the reagent. We're adding water, we're adding acid. Yes. What is the source of the acid? Hydrogen. Good job. This you can use hydrogen ion. Because we add water. Does that make sense, right there? Okay. If you don't add water, do not use hydrogen ion. Right? Okay. All right. Well, I'll walk you through the first one. Okay. So the goal is from acetal, gonna go to the ketone. Acetone. Go through halfway heading acetone. Okay. All right. The first is adding acid for chlorination. We have our that as a hydrogen ion. So equal to proton. Okay. All right. That guy gonna come off. So if you remember drawing the mechanism of acetal formation, we tracking backward. Everything reverses. Whatever happened when you go forward, it's a reverse order. They're going to go backward, reverse order. So we have chlorination, and then this guy going to get removed by the lone pair of the other methoxy group. Okay, from right here, nucleophilic going to get attacked by water. Here we go. Then I need to know right there, you have to be protein. That's halfway. Then you have to touch. You have it. Yeah. All right, so we're tracking backward basically. All right. All right. From hemiacetal. Which one I have to get rid of, the OH or the methoxy to go to the acetone? The methoxy group. What do you want to do with the methoxy? Protonated. Good job. This is a poor living group. If you want it to leave, it's gonna be better living group, right? You have to pronate it. What do you want to use to pronate that methoxy group? Hydrogen ion. Good job. Yeah. So you go back to the template with the pronated, right? And then we're ready to leave now. So push it with the lone pair of oxygen. What do you think you should do with this guy? Deprotonation. Good job. Why do you have to do deprotonation? What's the reason? Remove the positive, become neutral. You have to do that. Okay? Yeah.
Hydrogen H plus. What exactly is that again? What do you have?
Sulfuric acid, hydrochloric acid, FDR.
It's like a very cool.
Okay, all right. That's the hydrolysis of acetal. Now, compare contrast with the hydrolysis of imine. Okay, look first. So imine, we're gonna cut this bond. I'll show you guys this. We cut it in the double bond. All right. All right, we take it in mean when it goes to acetone. That's an acetone. Right, so this guy gonna come off. What happened at the first step? Yes. Chlorination, of course. We added an acid, use hydrogen ion, chlorinated. Okay, all right, become highly reactive now. So water comes in and attack. Even weak nucleophile like water can attack. Okay, all right, so you get almost halfway. So what do you think would happen with that water? Dechlorination. Good. You're gonna get a neutral first. You get carbonology. Go back to carbonology halfway. Okay, all right. Try to answer the question. I'm trying to see. We keep repeating the same. Can you see? We keep repeating the same stuff. Right? Try to let get you there. It's very I'll say logical and repetitive, right? And they all have patterns. All right, carbonology halfway. Answer my question. I'm gonna go to acetone. Which group has to lead? Nitrogen or oxygen? Nitrogen. What do you want to do with it? Chlorinated. Good job. Take chlorination on nitrogen. This guy can lead that. Look at that. And once you get to that, I assume you know what to do. Dechlorination. Excellent. So that's the hydrolysis of imine. That's imine. We got one more. I've got one more. We have acetal, we have imine. Next one, enamine. Okay, we're gonna do enamine this time. Okay. Oh, look at enamine. Now, enamine has a little twist at the beginning. Okay. Do you remember the last step of enamine formation? We do elimination. Remember that? Right? It's not dechlorination, it's elimination. When you go back, you go reverse. You have to track back every single step going backward. Okay? All right, so what are you going to do? Of course, that's going to turn to be oxygen. And look at this. There's a 2 hydrogen there, there's a 3 hydrogen there. The first step you're going to do is chlorination on that carbon. You have to put that proton back on. Because the last step, when you make this, you remove that proton. Okay? All right, so we're going to be a chlorination at the first step. All right, chlorination takes acid. Add water, add an acid, so of course, I don't need ion. Report it right there on that position. All right, we got that now. You can draw the resonance record. I'll show you that. You don't have to, but you can. Yeah. All right, take the water. Water can attack. Now look at reactive now. Water attack. And from right here, I think you know what to do with the water. What do you think happens with the water? Dechlorination. Good job, dechlorination. Halfway done. Carbonology. The rest shouldn't be that difficult. All right, we're gonna get rid of which one are we getting rid of? The nitrogen or the oxygen? The nitrogen. So what do you want to do with the nitrogen? Chlorination. Good job. Proton transfer. Chlorination on nitrogen. Okay, now keep them out. And the last one, come on. Dechlorination. Same stuff. I'm trying to show you what's it? For reaction, water, alcohol, primary amine, secondary amine, and then we have 3 hydrolysis. But can you see they have the same patterns? I they have the same patterns. Okay. Yeah.
What's up the lone pair from nitrogen moving down?
I'll answer you later. I'll ask you later. Okay. All right. Now, if you have to predict the product, again, do not waste your time. Draw the mechanism. I'm the one who have to do it. This one easier. Okay. All right. We're doing hydrolysis. So acetal going to come off. Acetal come off. Acetal enamine going to come off. Start with the top one. Okay. So the top one. This guy used to be a ketone. Does that make sense to you all? It used to be a ketone, right? Which carbon? From 1, 2, 3, 4. Which one used to be a ketone? Carbon 3. Right? So that's carbon. Gonna look at that carbon and guess what? That's the product. You don't have to draw the mechanism. Yeah? Of course, if the basic is a mechanism, right? But this one you don't have time to draw it. Yeah, that's how you do it. All right, look at this one. Where is the which carbon used to be a carbon? Can you point? Can you point? Can you point? We have the same one? Yeah, that one, right? So the product is like chlorpentanone. You can draw the actually glycol. Yeah, what's it? Yeah, it doesn't ask for the byproduct. And the draw street. Next one down, okay? Do you know which carbon used to be a carbon? How many carbons on that what this one is an aldehyde, right? If you remove the acetal, this acetal group, how many carbons on the aldehyde? Two. Good job. Two. Okay, that used to be an aldehyde. That's aldehyde. There we go. And ethylene glycol. You don't have to draw the ethylene glycol. Last one we have enamine. So which carbon used to be a carbonyl carbon? That one. See that? That one too. That's cyclohexanol. Probably one moment. Yeah. Sulfur. That's by introduction to the sulfur ring profile. What group is sulfur in the periodic table? Anyone remember? It's right below oxygen. Remember that? Oxygen and sulfur is in the same group. They have the same problem. They do the same thing. Guess what? Thioacetal, thiosulfur. It is used with acetal. Two sulfur with thioacetal have the same mechanism. I'm not repeating. Okay. What about it? What about it? We're going to like thioacetal. Okay. What do we use this for? Protecting growth. Now, here we go. It's better. It's going to get better. I'm telling you, like some better. Remember it is going to be acetal. Oxygen and oxygen. Okay. What condition is stable in? It's basic, right? If you add an acid, please pop off. It's like thioacetal, stable in both conditions. This is a good one. But hold on. If it's stable in both, how do you remove it? We need mercury chloride to remove it. We need that only one to remove it. Yeah. And one more thing. You can do this too. From cyclic acetal, you can remove the whole thing. By doing hydrogen and ready nickel go to thread chain alkane. Have you seen a reaction that do like this from ketone all the way to alkane? Clinker reduction, movement reduction, and this one, F3 total. We're gonna talk about it next time. Yeah. All right. Thanks for coming. Good luck tonight.